Hello, welcome to the talk on Biometric-Authenticated Searchable Encryption. This work is by Daniel Gardham, Mark Manulis and Catalin Dragan from the Surrey Centre for Cybersecurity. To summarise this presentation, I'll start by introducing searchable encryption and discuss existing techniques, extending to those that rely on passwords as an authentication mechanism. I will then motivate a biometric-based protocol and highlight the unique challenges this imposes. We will consider a naive approach and why this does not meet our design and security criteria. Next, we will take a look at the biometrics and introduce something called the Liveness assumption that will underpin the security arguments of our scheme. Finally, we conclude with an overview of the construction, its security theorems, and a description of a biometric update feature. Searchable encryption. Cloud services, such as Dropbox or Microsoft's OneDrive, offer convenient and on-demand network access to a centralized pool of resources. Currently, many users prefer to outsource data to the cloud in order to mitigate the burden of local storage. However, storing private data on remote servers poses privacy challenges. Searchable encryption, or SE, allows protection of users' sensitive data while preserving the ability to search on the server side. SE allows a server to search encrypted data without leaking information. On the left-hand side, we see a generic outsourcing protocol. The user authenticates himself to the server and stores a file along with an encrypted set of keywords. On the right-hand side is a generic retrieval protocol. Again, the user is authenticated and provides a set of keyword ciphertexts for the server to search on. Any match of the ciphertext returns the file to the user. Current constructions come in two flavors, asymmetric and symmetric based. Both require clients to manage cryptographic keys, which brings limitations for users who wish to use multiple devices to outsource and perform searches over encrypted data. To overcome the limitations of key management, password-authenticated keyword search was introduced, utilizing human memorable passwords to authenticate clients. The constructions rely on extracting a cryptographic key from a low-entropy password, where a distributed trust model across two servers prevents a single malicious server from brute forcing the low-entropy password. However, precisely due to their nature of being memorable, passwords are often reused in different contexts than their initial purpose. Moreover, research has shown that strict password policies that require the user to frequently update their password can further exacerbate this problem. This motivates alternative authentication techniques that are not required to be human memorable. In particular, in the domain of web authentication, the current trend is to move away from passwords to other forms of usable authentication factors. In this context, biometric data such as fingerprints, iris recognition, and facial imagery can be viewed as alternatives to passwords, especially since support for different types of biometrics on commodity user devices such as laptops, smartphones, and wearables is on the rise. We also note the attractive feature that the biometric data is not required to be stored or remembered by the user, yet remains readily available. A scheme that is entirely authenticated by biometrics would not require any key management, but to allow the scheme to be fully device agnostic, we will also enforce the design decision that the user is not expected to store any helper data. Therefore, to alleviate the limitations of existing searchable encryption schemes, we propose Biometric Authenticated Keyword Search, or BAKS for short. Like password-based protocols, our scheme will have to support key recovery from low-entropy sources, even in the presence of a malicious server that could perform brute force attacks. This suggests we will also need a distributed trust model as well. However, unlike passwords, biometric data is inherently noisy, which introduces unique challenges for recovery of cryptographic keys. Finally, we will need to overcome the challenge that biometric data may not be considered secret. A general approach might be to consider fuzzy extractors and combine with a searchable symmetric encryption scheme. A fuzzy extractor takes as input some noisy data and, along with some helper data, returns a deterministic string, provided the input data was sufficiently close to a template. A naive idea is to use a user's biometric processed by a fuzzy extractor to obtain a symmetric key, under which encrypted keywords could be outsourced to the server to perform the search. However, To practically use fuzzy extractors to source high-entropy symmetric keys, the biometric data itself must have certain qualities, i.e. that the minimum entropy of a substring is above a set threshold. Finding biometric data that meets this criteria can be challenging, as even the best source of biometric data, iris recognition, processed by a reasonable fuzzy extractor produces a key with entropy comparable to about 32 bits. Additionally, it is unclear how to apply these techniques to arbitrary types of biometric data and enforce the structure required by low entropy source distributions. Another aspect of the unsuitability of fuzzy extractors is its security assumptions. The security of this general approach would rely on the secrecy of the biometric data. While this assumption is widely used in academia, it is often too strong for real-world applications. We will see how to overcome this constraint in the next slide, but it is clear that the use of fuzzy extractors impose restrictions over the selection of biometric data, and that makes them unsuitable for our construction. Biometrics and the liveness assumption. A user's biometric data is modelled as a distribution D, from which an instance of a biometric reading is captured by sampling W from the distribution. We define a metric space on the sample space that allows us to measure the distance between two samples. Whilst the model we present for BACS suits any notion of distance, the protocol we will later present only considers the Hamming distance of two bit strings. To overcome biometric data secrecy, many practical applications for biometric authentication rely on mechanisms to check for the physical presence of the user. This can be enforced in practice with techniques such as software enhancement, e.g. pupil and eye movement in iris detection, hardware enhancements such as temperature or pulse, or via challenge response protocols, which could be facial expressions. This is known as the liveness assumption and has been adopted in e-passports as well as recent FIDO standards for web authentication and forms part of the ISO standards for biometric presentation attack detection. We note that realizing the liveness assumption will require some form of trusted hardware. However, the liveness assumption is only valid on the user device and enforced by the client. It does not prevent a malicious server from mounting brute force attacks on outsourced low entropy keys. In this work, we will model the assumption as a biometric oracle that takes as input a public biometric distribution and takes a fresh sample from it. It possibly performs some computations and outputs a result. Due to the noisy nature of biometric data, we consider two inherent error probabilities. Firstly, we have false acceptance, which is a probability that any two biometric samples from two distinct distributions have a minimum distance bound by a threshold t. In other words, the probability that two different individuals have very similar biometrics. This will have to be taken into account for our security definitions. Then we have false rejection, which is a probability that two samples from the same biometric are far enough apart that the measured distance is above t. This error probability will affect the definition of correctness for our scheme. We note that the value of this threshold t is dependent on the accuracy of the biometric scanner as well as some parameters set in the instantiated protocol. Biometric Authenticated Keyword Search. Here we have the model for our BACS scheme. The basic architecture comprises of three entities, the user and two servers, and is formed of three processes: register, outsource, and retrieve. A user runs register with both servers where they submit a commitment to a fresh biometric sample and secret share a cryptographic symmetric key. Outsource is an interactive protocol that allows a user to recover their secret key from their biometric sample and submit files with keywords encrypted under that key. Similarly, retrieval allows for reconstruction of the key if the biometric is accepted and performs a search of encrypted keywords and returns any matching files. We now look at the security properties for BACS. Firstly, we define indistinguishability against chosen keyword attack, or INCKA, which captures a scenario where an adversary is able to distinguish under which keyword a file has been outsourced. In the security game, the adversary chooses two keywords and is challenged to decide which of the two has been used to outsource a file. We allow the adversary to corrupt one of the two servers and any user other than for whom the challenge is embedded. BACS satisfies in CKA if the probability of success is within negligible distance of the false acceptance rate. This accounts for the scenario an adversary is able to recover the challenge user's key from a different biometric source. The second property we define is authentication. We allow the adversary to control one of the two servers, and it wins if it successfully outsources or retrieves a file on behalf of a user that it has not been corrupted. Again, we say that our scheme satisfies authentication if the probability of success in the described game is within negligible distance of the false acceptance rate. We now give a direct construction for our BACS scheme. As we saw on the previous slide, there are three protocols: register, outsource, and retrieve, but we present a common subroutine as a fourth algorithm called key reconstruction. On this slide, we have an overview of the protocols. The registration process generates discrete log keys for each of the servers S0 and S1, where the secret exponents are X0 and X1 respectively. It computes the shared public key as a product of these. It samples a high entropy symmetric key and computes secret shares Ki of this key K. It then further splits the shares Ki in a 2 of 2 secret sharing scheme between each of the servers. It computes a message authentication code for each of the shares, which will be used later to identify which parts of the biometric match. Finally, it samples and commits a biometric template from the user and sends all relevant components to each of the servers. To recover the symmetric key, a user samples its biometric data and commits to each bit of the sample and sends these to the servers. The servers combine this with the pre-registered shares of Ki and sends them back to the user with the previous MAC code. Using knowledge of the randomness used in the commitment, the user is able to remove this randomness from the key shares and check its validity against its corresponding MAC. If a sufficient number of shares are correct, i.e., if the biometric sample is sufficiently close to that which was registered, then the user is able to recompute the symmetric key. Highlighted in the blue boxes are the lines which utilize the liveness assumption through our biometric oracle. To outsource a file, the user executes the key reconstruction subroutine from the previous slide to obtain a symmetric key K. It then uses this key to derive a tag for each keyword associated with the file. This is done using standard pseudorandom and key derivation functions. The tag and file are sent to the servers, who check the validity of the tag and then store both in the database. During the retrieval phase, the user will repeat the key reconstruction and tag generation steps with keywords it wishes to search for. The servers again check the validity of the tag and compare to entries in its database. Any matches indicate a match in the keywords, and the file is sent to the user. Here, we've shown a naive approach for file recovery that is linear in the number of files stored in the database. In the paper, we go further and explain how one could improve the efficiency to be logarithmic in the size of the database, which matches state-of-the-art solutions. We do note, however, there are some functional trade-offs for this efficiency gain. Namely, for the approach we present, the servers are limited to maintaining append-only databases. That is, we lose the ability to remove files from the database. Security analysis. We show that our biometric keyword searchable encryption scheme offers authentication if the KDF functions are secure, the MAC is unforgeable, our secret sharing scheme is privacy, and the discrete log and liveness assumptions hold. If we also have that the PRF is pseudo-random, then the scheme is also secure against chosen keyword attacks. Our protocol offers a biometric update mechanism that allows a user to change their biometric. This may happen in the case when a user changes devices, say from fingerprint to iris recognition, or loses access to the initial biometric. To prevent the costly process of re-encrypting all keywords, we do not change the symmetric key. Instead, the user updates their biometric by computing a commitment to a fresh sample and sending this to the servers. This process can be completed without using the previously registered biometrics, but in such case would require alternative authentication channels. We briefly note here that our protocol can also be trivially extended to support searches on multiple keywords and also retrieval based on keywords that satisfy conjunctive, disjunctive, and subset type queries. So, to conclude, we've introduced Biometric Authenticated Keyword Search, a novel searchable encryption scheme that uses biometric data as the authentication mechanism for outsourcing and retrieval of files indexed by encrypted keywords. We accounted for the imperfections in the biometric measurements and designed BACs such that users can authenticate via biometric data that is similar to their template. This degree of similarity is modelled using threshold secret sharing techniques, and selecting the threshold involves at least considering the accuracy of the measuring device and the nature of the used biometric factors, e.g. fingerprint, iris, face, or voice. BACS employs a two-server architecture with the liveness assumption to provide security guarantees and doesn't assume the biometric data remains private. Moreover, BACS allows users to update their biometric templates without the need to re-encrypt the outsourced keywords, and provides support for multi-keyword outsourcing and search. BACS ensures that only legitimate users can outsource and retrieve files, and confidentiality of the outsourced keywords in the presence of at most one compromised server. Thanks for your attention. I'll be happy to take any questions.